Assalamualaikum and very good day to our lecturer and my fellow friends. So today we are going to present about our last experiment in the MM3531, which is heat conduction experiment. We are from section 3 and this is our group members. So my name is Muhammad Hazam bin Zahari. I will present to you about introduction and objective for this experiment. Next. For introduction, the first one is heat is carried by means of collision between rapidly moving molecules closer to the hot end of a body of matter and the slower molecules closer to the cool end. The second one is conduction is porous in gas because the molecules are relatively far apart and so interact less frequently than in solid and liquids. The third one is metal are the best conductors of heat because some of their electrons are able to move about relatively freely and can interact frequently by collision. The last one is thermal conductivity is thus a second order tensor, but in a material with cubic isotropy it reduced to a scalar. Next. For the objective, first, to study the thermal conductivity of heat transfer along a module of different elements. The last one is to study the thermal conductivity of heat transfer along a radial module. So the next part will be present by my friend. That's all from me.
All right. For literature review, T.B. Ferrari, S.H. Hara, J.L. Azian, L. Rocha, E.D. Paula, and M. Mulato evaluate a simple experiment that may be performed to assess thermal conductivity for different metallic materials and then compare with the theoretical model given by the Fourier's law of heat conduction in 2002. Using a scientific approach, the fundamental disparities between theory and experimental fact were investigated. They discovered that there are losses and other factors that must be considered when determining the thermal conductivity of a material, resulting in difference between theoretical and actual results. The schematic drawing for the experiment setup is shown in the top figure. Cup 1 is an aluminum cup that is filled with water and heated over a flame while being monitored by a thermometer. Cup 2 is made of telephone and filled with ice and water, with a thermometer monitoring the temperature. Through a metallic cylinder, heat is transported from cup 1 to cup 2. For experiment setup, we use laptop, heat power regulator, linear module, radial module, thermocouples, brass element, steel element, unbound heat sink paste, and water supply. Okay, next.
Okay, next we go to the experimental procedure. We have two experiments, that is linear conduction heat transfer and radial module. First, we go to the linear conduction heat transfer. First, the main switch is initially off. Then a brass conductor section, intermediate section is inserted into the linear module and clamped together. Two, the power supply turn on and the water is ensured flowing from the free end of the water pipe to the drain. The interval is checked. Three, the heater power control knob control panel turns to the fully anti-clockwise position and the sensor lead connected. For the power supply and the main switch is switched on, the digital readout will be illuminated. The heat conduction experiment software loaded. And number six, the heater power control turned to the 20 watts and sufficient time allowed for a steady state condition to be achieved before the temperature at all six sensor points and the input power reading on the wattmeter are recorded. This procedure can be repeated for other input power between 0 to 20. After each change, sufficient time must be allowed to achieve a steady state condition. Now we go to the experiment B, that is a radial module. First, the main switch is initially off. The stainless steel section or any other metal are insert into the linear module and clamped together. Number two, the water supply turn on and that water is ensured flowing from the free end of the water pipe to the drain. This should be checked at intervals. Number three, the heater power control knob control panel turn to the fully anti-clockwise position. And number four, the sensor lead are connected to the plug on the top of the linear conduction module. The left-handed sensor lead from the module connected to the place mark. This procedure can repeat for the remaining 5 sensor lead. Okay, number five, the power supply and the main switch is switched on and the digital readout will be illuminated. Number six, the heat conduction experiment software loaded. And lastly, turn the heater power control turn to the 20 watts and sufficient time allowed for steady state condition to be achieved before the temperature at all 6 point and input power reading on the wattmeter recorded. That's all from me. Thank you.
Good day, everyone. My name is Arindra Kartikeya. So today I'm going to explain about the result. Okay, this is the result for the linear module for stainless steel and brass. This is the data given by our lecturer, and then we just take the average point for each watt. For 5 watt, we take the average point, and then for 10 and 15 continuously we take the average reading. Next, from the data above we need to find the gradient. So we use the formula dt over dx. From that we find the temperature 1 minus with temperature 3, divide the distance, so we can get the gradient for the 5 watt, 10 watt and 15 watt. This is how we find the gradient for dt over dx value. The next, so next part will be the question required for the thermal conductivity. For thermal conductivity, the data is given that diameter is 0.025 millimeter, and then from the diameter we can calculate the area using the pi d square per 4. Using the formula we can get the area value. From that we can find the k. This is how we derive the formula for k. From the derivation we can find the thermal conductivity for 5 watt, 15 watt and then 10 watt. This is how we get the value for the thermal conductivity. Next, the same method goes to the same method we use to the brass. So for brass we need to find the gradient for e power 5 watt, because from the table given they have only one power only, so that is 5 watt. So for 5 watt we need to find the gradient and then continues by the thermal conductivity. Same method we use, same formula we use as the for the same formula we use for the value we need to find. for the gradient and then for thermal conductivity. Next. From the table, we need to plot a graph of temperature versus distance for each heater power value in one graph. So from the table above, we come out with the graph of 5, 10, and 15 watt. From the graph, we can conclude that it is shown that the temperature is decreasing toward the distance. This actually verifies the theory of heat conduction, where the transfer of energy from the more energetic particle of a substance to the adjacent less energetic ones as a result of interaction between particles. It is conducted in the direction of decreasing temperature, and the temperature gradient is negative when temperature decreases with increasing distance. Although the temperature is decreasing gradually, it is not closely similar to exact theoretical result. Theoretically, the heat conduction should be negatively linear. These results were mainly affected by the insufficient time taken for the recording of reading. Reading should be taken on nearly steady state condition. It is also possible that thermocouples are not configured correctly. This would have also disrupt the graph. Reading are taken during the steady state condition because there is no more temperature variation with time. Data collected would be more accurate. Next. This is the graph for the brass. So that's all from me. I just pass it to my friend. Thank you.
Okay, thank you, Samirash. So my name is Muhammad Saini, and I will discuss about the discussion for this experiment. So next, the first one is compress the calculated thermal conductivity to its typical value and describe the discrepancy factor. So first of all, the discrepancy factor is the factor that differentiate between our experimental data and the typical data. So the thermal conductivity for stainless steel is 20 watt per meter Kelvin, and for brass is 120 watt per meter Kelvin. So in our experiment, we got a value higher than the typical value for the stainless steel and lower a value for brass, thus showing that the typical value and the experimental value are very different. So the discrepancy factor in this experiment is the power voltage for each type of material, that is stainless steel and also brass. As you can see in our experiment, for stainless steel we use 3 power voltage, and for brass we use 1, and also their thermal conductivity. Next. So why the system of heat conduction in this experiment require cooling water flow? The first one is the water coolant was employed in this experiment to provide a steady state condition with temperature variations. However, the temperature should not be too hot to damage the result. And the water coolant is also used to keep the temperature down. Next. So this is the three reasons why thermal conductivity value for particular material is important in engineering field. The first one is a high thermal conductivity rating, means the material is a good heat conductor, whereas a low number means the substance is a poor heat conductor or insulator. Second reason is when designing a cooling system, the thermal conductivity value is crucial. So thermal conductivity value vary depending on the kind of system. And the last reason is aside from that, while designing insulation for a system, the thermal conductivity value is critical in selecting an appropriate material. Next. So this is the three examples of heat insulation method have been used in engineering nowadays. The first one is tank insulation method with cryogenic exposure. Ceramic fiber fabric such as aluminum borosilicate fabric is filled with a silicon elastomer to make a composite material for cryogenic exposure. The second example is loose fill insulation. It is suitable for use between the floor joints of unheated attics or between the side walls of homes that were not insulated after construction. And the last example is air gap insulation method. These insulators can boost chip speed by 35% while consuming 15% less power. That's all for me. I will pass to the next presenter. Thank you.
Hello everyone, I'm Ellen. As a conclusion, our experiment's outcome differed from what was expected from the theory because of the issue with the sensor's sensibility. Based to the graph, the gradient dx dt increases as the heater output increases because of the same material we utilized throughout the experiment. Overall, we learned how to run the conduction machine and analyzing the elements that influence thermal conductivity. That's all from us. Thank you.